My guest today is Professor Elizabeth Johnson, who is Assistant Professor of Medical Social Sciences and Pediatrics at the Weinberg College of Arts and Sciences at Northwestern University. Welcome, Elisa.
Thanks.
Is it Elisa or Lisa? Sorry.
Lisa. Lisa.
Say it again. Lisa. Okay.
Lisa, L-I-S-A. Yep.
Okay. So, so I got some of your papers, and these are really interesting topics. I know very little about them, but so I want to talk. I want to understand something. So I want to start with the 2022 paper, Structural and Functional Network Mechanisms of Rescuing Cognitive Control in Aging. So you say here age-related declines in cognitive control and ability critical in most daily tasks threaten individual independence. We previously showed in both older and younger adults that transcranial alternating current stimulation, TACS, can improve cognitive control with effects observed across neural regions distant from the stimulated site and frequencies outside the stimulated range. Yeah, this is really interesting. I mean, we have an aging population, and increasingly, this is it's a big issue, both economically and societally.
Yeah.
And if 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 an older person can take care of himself or herself, it has a huge effect. We are all sort of, you know, trending toward there. Um, and so any intervention and the transcranial alternating current stimulation is sort of it's not invasive, I would imagine, right? So let's
Right.
talk a little bit about what it is and what you have found there. Yeah.
Yeah, sure. So TACS, it's a form of transcranial electrical stimulation. Its sort of famous sibling is TDCS, which stands for direct current instead of alternating current. And classically, these are methods that, they literally apply electricity to your brain through the same sort of electrode that measures electricity in your brain. And classically, these are applied sort of in a rather blunt way. So like you'll get a big sponge with a big electrode on it and just kind of slap it right here or slap it right here and see what happens. For that reason, brain stimulation methods like this have gotten kind of a bad rap. But there is a lot of attention to how they could work and could work very well. And that brings us to the current study. And so I say, the blunt approach is to kind of put a big sponge and slap it on there and see what happens. With brain data, like simultaneously acquired scalp EEG data, or I should specify in the context of almost all of these studies, it is first you stimulate, then you measure, because of confounds in the electrical signal of doing both at the same time. But first you stimulate, then you measure. And the idea is if you are actually able to tap into a participant's sort of real brain region that you're trying to target, and in terms of TACS, actual frequency that I'm doing this because this is the sine wave showing a frequency, delta, alpha, theta, whatever, the actual frequency that brain region is kind of functioning at or speaking, the language it's speaking, then you should have effects. Say they are doing a task like cognitive control, which is what we did. The way we measured cognitive control here was actually using it was a driving simulation. So they actually had a little mini steering wheel and a computer screen, and they were seeing red and green lights. And if it was a red light, as you can imagine, you don't press a button. And if a green light, you do. And so they were cognitive control, driving while paying attention to these sort of lights flashing, if you will. Something like that tends to weigh on, say, a theta or alpha rhythm. Okay. So the goal with the TACS would be to tap into that rhythm, kind of hijack it, speed it up, not speed it up, kind of just increase its power, and then see if they get better at the task.
It's like a battery running out of power. You can probably just boost it a little bit
it's a lot
somehow.
like that. Yeah. But classically, what a lot of the literature shows is that these approaches tend to have either kind of mixed effects or very subtle effects at the group level, and that's why these methods do not always get the best people don't feel great about them. So one of the goals that we had here was to identify the individual differences and see what works, with the ultimate goal of actually being able to individually target these things.
Yeah.
And I see you waiting to ask a question.
So I don't know if I'm thinking about this correctly. So as an engineer, I would have thought that alternating current would be sort of disruptive to the brain. I know nothing about the brain, by the way. So, but alternating current stimulation, and we talk about, I think, direct current stimulation later, but the alternating current stimulation, and you're finding positive effects of this methodology, right?
Yeah, so I think what you're tapping into here is that, right, so our different brain regions during the performance of different tasks and stuff, they sort of have a dominant frequency.
Okay.
That's a little bit oversimplified, but not too much. And so, ways to think about this are, if you actually look at a rodent hippocampus, you're seeing a theta wave if you're recording directly from a rodent hippocampus.
So there's a frequency issue here. Yeah, okay.
Yeah, and there is almost always a dominant frequency. It's kind of a rodent hippocampus you will see a sine wave at like 6, 7 hertz, 6, 7, 8 hertz. For a person with scalp EEG, you may see a pretty dominant occipital alpha rhythm, sometimes even in the raw signal. So that's like a 10 hertz rhythm. That is most prominent actually when people are not doing much of anything, when they're just sitting there with their eyes shut.
Is it same for all humans, or do we find a variation?
There's a lot of variation. So it's like yes and no. You may see an alpha rhythm in just about all humans at rest, but the shape and exact frequency of that alpha rhythm will differ. So the alpha band goes, say, 7-ish to 14-ish hertz. My peak may be, I actually don't know. Maybe it's 10.2 and yours is 10.8.
So you need a knob to sort of fine tune it?
Yeah. And that's what we're trying to do with tax. So current tax approaches, classic tax approaches, if you're trying to hit the alpha rhythm, you just hit the brain with 10 hertz and hope it works. We find we actually want to delineate the individual differences, see for whom does it work to hit it with 10 hertz and why. What do we do with the rest? Yeah. And with the goal, at least in our work, to actually come up with personalized brain stimulation. So I gave the example of maybe I'm 10.2 and you're 10.8. That means you would hit, to target my brain, you'd hit me with a 10.2 rhythm and you with a 10.8 rhythm. Something like that. What we did in this paper was find that a lot of the determinants of what worked had to do with the brain networks and the task you were performing.
So when you sort of start this process, so you have some measurements. Can those measurements tell us what the optimum frequency might be?
Yeah, you can do I like to call it kind of a quick and dirty analysis that you can do really almost on the fly. You remove some of the worst noise, an EEG signal if somebody's sneezing or something, that is not salvageable. And then you can do a quick Fourier transform, power spectral distribution, whatever you want. Get that, frequency. I don't know, you say measure the frequencies from about 1 to 30 hertz, and there should be a little bump somewhere in the vicinity of 10 hertz, be it anywhere between 7 and 14, and that is that person's alpha peak.
7 and 14, okay. And that's sort of a constant. So if I look at person X and person Y, I can sort of categorize them into some frequency regime, like 10.2 and 7.8.
I don't love that language just for fear of categorizing people based on some sort of arbitrary measure.
Yes.
But yeah, you can usually pick that up and find that it should be reliable, at least for that person's session performing that task at that time. It can change, as you can imagine, if somebody's caffeinated or underslept or any number of factors.
But it's reliably sort of deterministic. for an individual. And so that makes the problem a little bit easier in the sense that, if you get the individual to the lab and you have this dial,
Mhm.
an optimization dial, so to speak,
Yeah.
and you can turn it, or maybe you can deploy AI on it, a little bit, and
Good.
say, let the AI sort of figure out what the
Telling
optimization.
AI how to do quick and dirty analysis is pretty straightforward. Yeah. Um,
Yeah, it's really interesting. So
Something else cool I will actually
yeah,
say is there are some predictors. We have
yeah,
found age to be a big one. So older adults actually tend to have a slowing of dominant rhythms. There
okay.
are still individual differences, but by and large, you take somebody in our study here, like a 70-year-old compared to a 20-year-old, their alpha rhythm should be a little slower.
So longitudinally, so if you follow an individual over his or her sort of lifespan, you will see this frequency is sort of going down
You'll
over
see it
time.
speed up rapidly in childhood, taper off in adolescence,
Yeah,
remain relatively stable, and then do this in older adulthood. It'll
and
graduate.
it goes down. Okay. So the frequency goes down, which would mean that the wavelength goes up, or it doesn't.
I mean by
In
wavelength.
this context, it doesn't make any sense. Okay, all right. So frequency goes down. So frequency goes down means things are getting processed slower.
That's a good way to think about it. There's sort of
Okay.
a whole issue of like we can measure the frequency. What does it do? What does it mean? Is a
Yeah.
whole nother can of worms. But that is absolutely a dominant model of like your alpha rhythm allows you to sample the visual world. And so if it's slower, you're sampling the visual world a little less
Yeah. So
potentially.
talk a little bit about the study. So the TACS, you have found positive effects of this non-invasive therapy.
Yeah.
You put some things on the skull or whatever, and then you can sort of, it's a bit like recharging your brain, isn't it? I mean, uh, especially when you get older. I mean, I'm in that cohort now. I would love this. I would love to get my brain recharged.
This is some of the goal, right? So these
Yeah,
these these TES methods, so TACS and TDCS, they're very low currents. They're safe. They're arguably so safe they maybe don't do anything. I say arguably because we found a way to make them do stuff, but that's why they've had a bad rap. But they're
yeah,
safe. They're cheap. These one of these devices is, I don't know. They're relatively cheap in the research world, kind of like scalp EEG. You measure current, you deliver current. They're safe, and they offer a potential non-pharmacological alternative
mm,
to maintaining, certain types of cognitive or motor performance after insult, like a brain damage or just with natural aging or something else. And
yeah.
so what we're working to do is come up with an actual protocol that would make that work. These studies are proof of concept. We're taking a set of, say, 20 or 40 people, putting them through
Mm.
a very strict regimen and seeing who responds to what, and defining for whom this works and for whom it doesn't, and therefore what we should do about it.
So am I understanding this correctly? So if you look at an individual longitudinally, sort of things sort of decline. So the older individual will get a higher effect on this therapy, right?
You mean because they have more that their brain needs to do,
Yeah,
kind of more to compensate for?
yeah.
I think that's the hope.
Okay.
That is not always what we've found.
So what do you find? Yeah, so it's interesting. So you look at a 20 or 25, 30-year old, TACS could actually boost them too,
Yeah.
potentially.
Oh yeah. It's easier to tap into a young, healthy brain, honestly.
Wow, okay.
And so there is a sort of finding that we've found with a few papers now of sort of the rich get richer, which is not what you want.
Mm.
Right. So when I say the rich get richer, we have done this in a few different papers. We've related it to just education. So literally, if you've gone to college, you are more likely to be receptive to this type of brain stimulation as an older adult than if you
Oh,
haven't
wow.
undergone
Okay. So
education.
that's a different axis altogether. So
Yeah.
it's sort of a preconditioned brain is more susceptible to boosting.
Yeah. Sort of
Yeah,
more malleable, more receptive.
more receptive.
But when we think about
Right.
it, we want to go why. So having this demographic variable like education, that may be
Yeah.
useful for determining for whom such a treatment may be effective, but we want to know why as the scientists. So we get in there. And what we've found in now this paper with education and the one that you brought up here about cognitive control with the driving simulation is that brain network integrity is a really good predictor. So if you have more white matter integrity, that means stronger pathways between different brain regions. You are more likely to respond to this type of treatment. And that is the same reason I believe that in young adults, it's just easier.
Yeah. I mean, the education axis is quite interesting. So I don't know if this is the case, Elisa. So I've seen some studies that showed that people who are highly educated, engineers, doctors, PhDs,
Mhm.
tend to tend to get into Alzheimer's more frequently than otherwise. Um, so, in some sense, that is contradictory to this observation, right?
You think so? I mean, you think
No.
that's really the case, or that's sort of anecdotally what you've seemed to have encountered?
Yeah. So I don't know. I mean, I've seen some. So the hypothesis was that a flexible brain, so you go from subject to subject, area to area. You sort of, you play some music, you
Mm.
write some literature, and you do some engineering structures, and you cure some people.
Yeah.
You have a very flexible brain as opposed to somebody sort of, diving deep into a discipline. They seem to have a little bit more of a rigid brain, and that seems to get you to dementia more often than not. I don't really have the data. I'm speculating here. Yeah.
I think if that's anecdotal, I want to raise the specter that it's sort of almost as you maybe more conscientious people are more in tune to their memories and worried about it.
Hmm.
Because the population level data do not show that
Don't show
more
that.
education means more dementia. They show
Okay.
quite the opposite. But I kind of know what you're talking about. When I tell people in the wild what I do, they tend to say, "How am I doing?" And I'm like, I'm at no place. No, I am not in a place to diagnose you, nor would I ever do that on the fly at a coffee shop or something. But
Yeah.
I'm saying you're asking. But no, the data really show something quite different, which is education is actually a good predictor of cognitive reserve in aging.
Cognitive reserve. So, I mean, you're showing two things. One is a cognitive reserve question.
Mhm.
It's a broad question, but you're also saying that TACS could actually boost those brains
Yeah,
that is sort of susceptible to
yeah,
that with higher education, right? Yeah.
yeah. So let's go back to that point. I said
Yeah.
my sort of working theory is it has to do with the integrity of our brain networks. Now, education, cognitive reserve, intimately linked to the integrity of our brain networks.
Hmm.
So that's me trying to find a sort of physical function and functional mechanism between the demographic observation and the finding that brainstem works better. Um,
Yeah. Is your lab set up in Evanston to take external subjects? I would love to come to Evanston and get my boost. Is
well,
that
we're
possible?
actually downtown Chicago, so it's even
Oh,
easier
you're
for you to
downtown
get
here.
here. But we've got a system. Come in. I'll even tell you your peak alpha. Um, I was guessing, we'll see, but we can totally do that. What I did want to point out is, although most of the data is pointing to a sort of rich get richer, one
Yeah.
of the main reasons we do this type of work is to figure out what needs to be done for the rest. So the rich get richer is not those who might need this,
Hmm.
right? Those who might need this are those who have farther to improve. And for that, we actually, in one of the papers I sent, found a kind of potentially alternate route that was independent of the effective education,
Yeah.
independent of brain network integrity, that had to do with actually a mechanism called a phenomenon, I should say, called cross-frequency coupling, which I don't need
Yeah.
to really unpack here, but it's something going on in terms of electrophysiology about organizing information within and between brain regions, and that actually may be a means by which speed is improved in an indirect route to improve performance. And so we did find a way in which those who were not the rich here were able to still improve. Why that's really exciting is because it means that our approach, if we ever want to make this effective in an applied or clinical setting, is to treat based on easy demographic variables like did you go to college or not. Maybe kind of take a slightly different approach. Maybe put those electrodes elsewhere on the brain. Maybe zap them for longer. Maybe zap them at 2 frequencies. We can cause cross-frequency coupling to increase if we are intentionally targeting it.
So you had a sort of similar paper. So I want to go to another one. So individual predictors and electrophysiological signatures of working memory enhancement in aging. So you say here a primary goal of translational neuroscience is to identify the neural mechanisms of age-related cognitive decline and develop protocols to maximally improve cognition. Here we demonstrate how the interventions that apply non-invasive neurostimulation to older adults improve working memory. Yeah, so I spent some time in the pharmaceutical industry, and the chemical interventions in the CNS system haven't been exceptionally good, to put it mildly.
They're dangerous and very expensive.
And so this, no, I always, I always argued that the human body is a electrochemical magnetic system. We only try to influence it through chemical means, but magnetism and electricity should be on the table to think about it.
Yeah.
And so working memory. I mean, working memory is a pretty important thing, isn't it? I mean, I was talking to some other neuroscientist a few weeks ago, and we're talking about just only 4 or 5 things that you keep in the working memory. It's like a cache in a $10 computer. And you flush it out after 5 minutes, 10 minutes, 15 minutes. But the working memory is so important on how you function as a human being, right? So we can actually improve working memory.
Yeah. So this is the pair of papers I sent you about how we can use brainstem to improve basic cognitive functions. And we're targeting a slightly different function here than cognitive control. Instead of your ability to sort of start and stop while doing something else, we are targeting now how much information you can kind of maintain at one time. Yeah. And working memory can also just be thought of as thinking. Honestly, how much can you really think about at one time? And attempts to quantify it have led us to anywhere from 3 to 5 pieces of complex information to up to 9 pieces of simple information. So if you've ever heard of the magical number 7 plus or minus 2, that is our working memory for, say, a phone number. We rarely have to remember phone numbers anymore in 2025, but I am, 7 digits is a phone number. You can remember that while dialing it back in the day.
But I don't know if they're independent pieces of information, though. It is sort of encoded into a single.
That is an important point. Yeah. It's the idea of chunking here.
Yes. Chunking, yes.
Like putting pieces together. So, right, say you have the date 1776. I already chunked it right there. If you're remembering 1776, that is 4 pieces of information. If you know that that's a year, all of a sudden it's 1776. That's 2 pieces of information. If you're American and you know how important that year was, it become 1 piece of information, right? So that's the idea. A more complex piece of information, we can maintain a little less of that in mind at a time. But so we were doing something very similar in this study, was trying to figure out in older adults who
Yeah.
is most likely to respond to the same kind of targeted intervention in the context of working memory.
It's more likely to. So, is there any implication that so here you're using direct current stimulation?
Yeah.
Is there any implication to the paper that we talked about before?
So these are very similar approaches. They're both electrical
Yeah.
stimulation. TACS, it is sending rhythmic waves, and TDCS is kind of a constant kind of. And the idea is TDCS increases the chance of neurons firing in the targeted region. So
Yeah.
it is not designed to tap into an intrinsic or dominant theta or alpha or some kind of rhythm. It is simply trying to kind of jumpstart that brain region.
Hmm.
And one of the reasons that it's great is because you don't need additional data to figure out what that person's dominant frequency is.
Okay.
And so you can just kind of go do TDCS, let the brain do what it needs to do. And it was used more often than TACS until very recently. There's kind of been a little bit of a shift because almost without exception, these devices can do both, and you just switch it to do one or the other depending on your goals. But we have found, I would say my conclusions at least are pretty similar. You're still trying to target a brain region in a person, and we wanted to see who was most likely to respond.
So are these effects permanent? What I mean is that, suppose I walk into your Chicago lab and you put some things on my brain, get my brain stimulated. Can I walk out and thinking that now my working memory is better?
Oh, I
And
wish. Right? So let me tell you, we get very excited when there are still measurable effects an hour after stimulation.
okay,
And we've done studies before that does longitudinal stimulation, so sort of a repeated protocol day after day for a week.
yeah,
We'll be really stoked to see that there's still effects a month later.
a month later.
A
Okay,
month later,
so
it can happen.
that's pretty good.
Chances are we got to tap into it, though. You sort of need to be doing the same task again. Usually it's rare that you just, I've not heard of an instance of this. I shouldn't say it doesn't exist, but I'm not familiar with any where someone gets brain stimulation one day and their brain is forever changed. That's not really a thing. But the goal of this type of work would be to determine what kind of sort of repeated stimulation regimen they might need to have long-term benefit.
Yeah, so when we do a chemical intervention, we have to take a tablet every day, and it is not significantly different. Um, you know, you get this idea to Apple, maybe they'll create a device that you can attach to your brain and or not
Yeah.
attach to your brain, but you put it on at 8 a.m. every day. It's just like taking a pill.
Yeah.
It's not substantially different. And the bad thing about the pill is that we don't actually know how the thing is going to get out of the system and how long it takes. Here, it's much more targeted, isn't it? We could actually make people remember things better, behave better. Um, so I think there has to be a huge focus on this. I think,
I
yeah.
think there is, increased attention to this idea of a precision medicine approach to brain stimulation. And that is a goal. It's like, see for what sort of problem you want to fix. Maybe it's gradual declines in working memory with age. That would be what we were going for here, or gradual declines in cognitive control with age. You
Yeah.
sort of try to hijack it early before it's gone too far and aim for maintenance, like preventing a decline with repeated stimulation.
Oh, yeah.
But it's not just, this is an important point. You're not just sitting there taking it. You're doing a task while you do this. So it is working with your brain to do a working memory task. So for
Yeah.
that
So
to
there's a
really work,
preventative. Yeah. So sorry to interrupt. So there's a preventative aspect to this. So if you sort of say maybe 25, 30, 35. I don't know what the right number is. Um, if you get into this, it's like exercising. You exercise your body and you get cardiovascular benefits. If you exercise your brain,
Yeah,
you get it's a
yeah,
similar thing, right? So
it is.
yeah.
So I can tell you, to put that in more concrete terms, this initial study with the driving simulation and the stop and go, that was a training game, actually, this driving game that was first published in 2013 in Nature as
Hmm.
a training regimen for older adults. And I believe, I am sorry, I'm going to get the details not quite right. This is out of Adam Gazzali's lab at University of California, San Francisco. Um, I believe it was 6 weeks of training
Hmm.
on adaptive multitasking training. And so our proof of concept goal with this study was to use tax to speed that 6 weeks up into one. You still had to do the task. You still had to do the week of training, but you didn't
Hmm.
have to do 6 weeks of training.
Yeah.
So in that way, it is sort of similar. And you ask other questions like, yes, you work out one time. Is that going to forever change your body? No. You work out repeatedly and it will,
Hmm.
right? It is sort of like training your brain. But the question is, what sort of task do people need to be engaged in for this to become actually useful in the world, right?
Hmm.
So this is a sort of elusive concept of transfer, of you hope that if somebody gets better at a working memory task, that therefore their working memory will be better.
Yes. Let me
Trying
ask
to
you.
the right task, to really
Right.
tackle that.
So let me ask you sort of a loaded question.
Mhm.
So this has a drug effect too. So suppose you invent a machine that you put on, and your working memory improves. And I'm thinking about kids here, you know.
Yeah,
So we have chemical agents like amphetamines and other things that kids take to get ahead on exams and things like that, right? So
like Ritalin,
this could
Adderall. Like, what are the kids taking these days?
no, not in Northwestern. I'm thinking about other universities, but um, so this could have some sort of a negative aspect too, right? I mean, if you invent something that is reliably works to increase your working memory, to increase your cognition, that has a lot of utility for younger people too, not just for older folks.
It does. Yeah. And, currently, brain stimulation just for the sake of it is not legal in children. You need
Hmm.
some sort of clinical indication. And so all of these studies we've done have been in adults. Um, but, you know, I'd say it's probably safer than popping, an Adderall that's not prescribed. Like, not saying they should get into it, but other ways that people can very healthily, legally, and in an okay way do this are things like these brain training games.
Hmm.
Many of them don't work, but the concept is sound. You're like, it's even as simple as maybe you play a game, or maybe you are somebody who religiously does the crossword every day. You are exercising your brain when you do that, and that is
So,
good.
so who is the regulatory agency around this? Is it the FDA or
Should
somebody
be the
else?
FDA. I mean, these devices we purchase need to be FDA approved.
So let me go to another paper, a little bit more technical. So dissociable oscillatory theta signatures of memory formation in the developing brain. So understanding complex human brain functions is critically informed by studying such functions during development. Here we address a major gap in models of human memory by leveraging rare direct electrophysiological recordings from children. Specifically, memory relies on interactions between the medial temporal lobe (MTL) and prefrontal cortex (PFC), and the maturation of these interactions is posited to play a key role in supporting memory development. Yeah, so it's a bit getting into the hardware,
Yeah, mouthful.
hardware of the thing. I mean, anybody who has watched a kid growing up, um, it's such an amazing thing, isn't it? I mean, they soak in all this information and they seem to connect it all together. And every minute, every hour, every day, they get better. And so, yeah, so that's a really nice phase to study, isn't it? How the brain develops. Yeah.
So, as I think about this type of work, so I love that you jumped to our developmental work, which is something we really are focusing on in our group these days and is very dear to my heart. Um, Kids are learning machines. As you said, they can remember stuff. They've got it. But what we are taking here is both a tool and a really important point of practical application is from childhood, so call it 5, 6-ish,
Yeah.
into young adulthood, they are improving remarkably at
Mm,
almost every complex cognitive function.
mm,
Our particular window into this has been memory, but this absolutely applies to attention, to cognitive control, to language, to insert here.
yeah.
And so we study brain development over that age range from, say, about age 5. And in this paper, we went up to 21. In current work, we're going up to 55. It's super cool coming
Mm,
out soon, but I'll stick to this paper because those papers aren't out yet.
mm,
Um, when we look at this 15-year period to see, okay, behavior, meaning performance on our particular memory task, and this was a long-term memory task, not
yeah.
working, a very simple one where you're shown images and then you're asked whether you've recognized the images after the fact. That kids, adolescents, young adults' ability to do that predictably improves with age. It's not
Yeah.
super dramatic, but it does. And over that
Mm,
time period, we know there's a whole lot going on in brain development, right? A lot of the early rapid stuff has happened. Motor function is in a not final, well, there is no final, but it's in a pretty good place. Visual, olfactory, sensory, everything there is pretty good. But these
mm,
complex cognitive functions that rely on you know, long range brain network connections and other microstructural nuances that are happening over a more what's called protracted period. And that's what I mean by this sort of 15+ year span. Those are
mm,
continuing to develop along with complex cognitive functions. On the one hand, that's why it's so important to go to school, to be working your brain while that's happening. On the other, it gives us a really, really fascinating window into how these complex functions work. So in
mm.
this paper, we wanted to begin unpacking some of that. So I think everyone under the sun knows that you need the hippocampus to form memories
Yeah.
for events in your own lives. We all know that. What we don't know is in the human brain exactly what's happening within the hippocampus that makes the
Mm.
memories. There's some data, coming out in adults, but what was going on in development, a huge black box. So we started getting into that. I think you're going to ask something.
Yeah. So I don't know if this is in your research, but so the 5 to 20 range, age range, there are a lot of things going on there. Is it because the brain is learning to communicate with itself? And so, I mean, you talk about this MTL-PFC interactions here. Um, is it is it that the brain is finally recognizing that, hey, I got a lot of stuff here, you know, I just have to connect it all together to make a really good computer. Is
I'm
that what's
sure
going
that's
on?
part of it. I wouldn't say it's all your brain realizing it. A lot of it is sort of structurally just happening. That is part of brain maturation.
Yeah.
Is these white matter connections. So we in this paper talked about one called the cingulum bundle. I think of that as sort of the long posterior route from your medial temporal lobe, which is kind of inside from your ear,
Yeah.
back through the parietal cortex and up to the frontal lobe, like that.
Mm.
And that is a big long range white matter tract that honestly is undergoing microstructural change that makes it more, that strengthens its integrity up until our mid 30s.
So it's
That is actually
programmatic.
probably one of the longest. Um,
It's
that's
programmatic in the sense that neurons are moving into positions and connecting it all together. So it's not, obviously it's not intentional. It's sort of programmatic, right?
it's both, right? I think, and it's really, I can't tell you. It's not definitively known by simply looking at brain measures, but there's a lot of evidence to show that, gene environment interactions go both ways. So that's why
So in your final thought here, you say here, our findings establish system level dynamics of memory formation and suggest that MTL, which is medial temporal lobe, and PFC, which is prefrontal cortex, interact via increasingly dissociable mechanisms as memory improves across development.
Yeah.
So it's a bit of a cooperation. As I say, people say I have 5 people living in my brain, and they have to cooperate to make it all happen, right?
Yeah. So I'll unpack that a little bit because that is a very loaded sentence. This does go back to what we were talking about with the aging studies, actually, about people's brains at different ages and different regions having different dominant frequencies. So something that we discovered in this work. So we used a method, by the way, called intracranial electrophysiology. These are basically EEG probes, but implanted directly on the cortical surface in the case of this study. They also can be implanted like skewers, say, to target deeper brain regions. That means that this study was the first published, to my knowledge, measure that directly measured medial temporal lobe activity in children. This is part of why this paper was so exciting. It was foundational, although it has an N of 21. We are doing much better now as we've upped that sample size, but it was foundational work with this method in children. So what we found was that in the medial temporal lobe, the theta rhythm, the dominant kind of 6-7 hertz rhythm that we classically think of as theta, got that way over this 15-year period. It maybe started out more like 4 or 5 and ended up more like 6 or 7. At the same time, there was a slower theta rhythm that started out more like 3 or 4 and ended more like 2 or 3. So these theta rhythms, they start a little bit jumbled and they end up dissociable. And so what we think, that was something we could directly measure, but the rest is speculation, right? Given that what these rhythms were doing was providing synchrony between the frontal lobe, prefrontal cortex in our case, and the cortical medial temporal lobe, because what they were doing was allowing these regions to be in sync. And that synchronization, the more you had of it, the better your memory was on our task. There's a lot of different data streams coming in that we made sense of here. What we believe is that with that sort of protracted development through adolescence, those who are doing well end up with this very well-functioning kind of multiplexed or 2 things happening at once kind of communication.
So this paper, the paper that we've been talking about, is saying we focus on episodic memory, the ability to remember detailed information about past experiences, which improves from childhood into adulthood. We review memory effects based on broadband spectral power and emphasize the importance of isolating narrow band oscillations from broadband activity to determine mechanisms of neural coordination within and between brain regions. So my bias is that we're never going to understand the brain. It just seems too complex to even start.
We're limited by our own brains. We can't do it.
Yes. But it is good to sort of dig around on the periphery, to try to see what the hardware is doing. But it's really tough, isn't it? I mean, this is why we haven't made much progress in artificial intelligence, quote unquote.
People another hour. We could really get into that one, but it's hard. I mean, the brain it's probably one of the most complicated things we've tried to understand. And I say that knowing that we also have things like astronomy.
Well, in astronomy, we don't understand.
We have to try, right? It is who we are, quite literally. If people have healthy brains, they are better people. They're more independent people. They're happier people. Everything, we need it for medicine, we need it for society, and then there is the whole brand new world that we're dealing with right now, which is if we're ever going to program a non-biological brain to be, I don't know, God forbid, trustworthy,
Yeah.
we should try to understand the biological one because we kind of are finding it acts pretty similarly.
Yes. So I want to finish up with this. So you say here when we then review evidence of developmental variability
Mhm.
in neurooscillations and present emerging evidence linking the development of neurooscillations to the development of memory. So when you say neural oscillations, are we thinking about, are we talking about sort of the frequency?
Yeah, exactly what I mean. It's the same sort of theta or alpha rhythm that we talked about in context of aging.
And we see a lot of variability in it. So from an evolutionary perspective, I'm stretching this. I have no clue actually. Do we have any hypothesis why certain brains are the way they are and certain others are not?
You know, the question of why is such a fun one, but a tough one, right? We can show that
But we
by,
don't know
by
why.
simply
Yeah.
measuring behavior, by measuring brain activity with these intracranial recordings and these recordings combining scalp EEG with brain stimulation to perturb the system and see what happens. We
Yeah.
can start to get at how. And that's really where our group comes in, is like, we know that.
Mm.
We want to move from it's happening to how. And we can start to speculate about the why.
Yeah.
I will say, you bring up evolution. Our brains are by no means the end product of a perfect evolutionary trajectory. We're not the end product of
It's
anything.
an
It's
accumulation of
happening.
errors. Yeah.
Yeah, it's sort of what it's what happened. So how does it work? Um,
So, um, I was just thinking, there's so what your research shows is that there's sort of a brain genome. So, if we think about genome, sort of the hardware of the human system, but the brain has its own genome in some ways, right? So the frequencies are different. Um, the areas that people focus on are different. The brain is sort of sitting there, doing all this stuff. And so it's a I don't know. I mean, there could be a brain type genome. Do you think?
well, I mean, we think of it, I mean, there's always a gene environment interaction, right?
Yeah.
So there may be, as we talked about with, say, individual differences in the frequency of your alpha rhythm, right?
Yeah.
On the one hand, everybody has an alpha rhythm. If they don't, well, I shouldn't say that. Every healthy brain has an
If they're living, yeah.
every healthy awake brain has an alpha
Yes.
rhythm. If you're not seeing it, it is most likely a problem with your head cap EEG setup. Like, but the way that the character of that alpha rhythm will
Mm.
differ from one person to the next. Some of that is explainable by simply age, which would go with your theory about it being genetic.
Yeah.
Um, uh, Other of it we can predict, actually. Like I said, if you've had a lot of coffee, you will probably have a different alpha rhythm. So
Mm.
that's yourself on different days.
Yeah.
If you were very underslept, you may have a different alpha rhythm. If you've just run a marathon, you may have a different,
Mm.
so, and that's not
It's
just
highly
the day-to-day
variable. Yeah.
variation. That will end up impacting how your alpha rhythm works over time. So gene
Yeah.
environment interactions go both ways.
So this is a little bit morbid, but so we have coma patients, and um, could your technology and your research tell us if there's somebody in there or not?
Hmm. Not directly.
Okay.
Nothing we're doing in this lab do I want to have linked to that, because no. But a sort of approach of peering into the brain without an overt behavioral response,
Mm.
absolutely. And
Mm.
so what we need are to define the indicators of,
Yeah.
is somebody in there? And
Yeah.
then can we measure and test those? Absolutely. And we are not a lab that's working on defining those indicators, so I don't want to speak more specifically. There are others doing that, but absolutely there is evidence that people who are in a coma may have hearing ability. There's evidence because you see changes in their brain when a sound is played compared to when a sound is not played.
Yeah.
Does that mean they're conscious? That's a whole issue of semantics.
Yeah.
But you can
I mean,
see brain without any
there's legal
behavioral.
implications, right? So if the technology can, at some high confidence, tell us there is a difference between X and Y,
Mm,
both patients being in coma,
mhm.
um, I think that's quite a useful technology, isn't it? I mean,
Yes.
I'm just thinking, yeah.
Anything that allows us to reliably measure what's under the hood, or a black box, or whatever metaphor you want to make there,
Yes,
as long
yes.
as we know what we're looking for, that's where the basic science is necessary. We need a better understanding of the brain to know what we're looking for. And our group and collaborators are really working on that in the domain of lifespan, age-related variability, and cognitive performance. But absolutely, there are labs considering this in the context of, say, basic sensory motor function in coma and stuff like that. But the idea is you need the science to tell you what you're looking for. Then
Yeah.
absolutely the technology exists if applied appropriately.
Excellent. Yeah, so I had to let you go, but this has been great.
Yeah, it
Yeah,
was a
thanks
great
so
high
much for
note to
spending.
end on.
Yeah, thanks so much for spending time with me.
Okay, thank you so much.